Hello out there, fellow environmental engineers. Today we are back to continue our ongoing series on pipe flow. And before we do, though, we would like to take a moment, seeing as here in America it's Thanksgiving Day, we want to extend our thank you to everyone who's been part of the High Water Studio community, High Water Studio viewers, and wish everyone who celebrates Thanksgiving a wonderful time with their families. And to every other country out there, almost every country, every custom has some kind of fall harvest festival that they enjoy and celebrate. So everybody in the world, from us to you, we hope you're having a great fall and happy harvest. Okay, so let's get back to today's lecture, which is going to be one of my favorite topics in pipe flow, is parallel pipe flow. And this is this topic on, we've talked a lot about in earlier videos how to solve essentially between 2 points, or the conditions at one point and the condition at some other point, right? But that doesn't tell us anything about what's going on within the system. So today we're going to start taking a look more deeply into these systems and looking at what's going on in between these 2 points, especially when we have pipes in parallel, which obviously is going to get more complicated. So let's take a quick look here. Now, if you've looked at our other videos, if you've been keeping up with the series, or if you've studied hydraulics before, then you probably know the first thing we're going to do is apply our energy equation, right? And we've done this before in a previous episode where we are looking at conditions between two reservoirs, right? So if you're not sure how to apply the energy equation between two reservoirs, that's our very first video in the series, I believe. So all we have to do here, because these reservoirs are essentially going to cancel out the rest of the energy equation, we know that our total head loss of the system is going to be equal to this change in elevation between the two surfaces. So in this case, Z1 minus Z2, which we are given is 100 feet. Okay, so that's pretty easy to find the total head loss of the system, but what we are interested in is what is VA, VB, velocity of pipe A, velocity of pipe B, and velocity of pipe C, which of course if you know that, then you also know flow rates in A, B, and C, total flow rate, you get all that information. Also head loss in A, head loss in B, and head loss in C. Okay, we want to find these. At least that's typically what you're asked. It could be that you're given some of this information and asked to find pipe diameters that will make that work, but typically this is what you're asked. So, okay, how do we do that? Now, before we even start specifically talking about parallel pipe flow, let's just have a quick reminder here that if we know the head loss, then from Hazen-Williams equation, we know that the head loss is the friction factor times the length of the pipe, the diameter of the pipe, divided by the diameter of the pipe, times the velocity squared over 2g, right? So essentially, if we know the pipe characteristics, the friction of the material, the length of the pipe, and diameter of the pipe, then it's really an equation about the velocity, right? Then head loss is dependent on velocity, which is the only thing that's going to really change over time, except potentially the friction factor over a long period of time. Okay, so how can we use this information to figure out some information about flow rates in A, B, and C? And there's three things you need to know about parallel pipe flow if you're going to try to solve one of these one of these types of problems. The first thing is, let's go ahead and start with the head loss relationship between pipe A and pipe B. So if you think about how do you develop a relationship between these head losses? Is it going to be, do you think it's going to be dependent on these characteristics of the pipe or the velocity Could one be more than the other? Is there a way to figure that out? And it turns out that if you think about it, now this is in steady state flow or at equilibrium is how you're, going to be solving one of these problems always. So at equilibrium, if you think about what happens if the system's in equilibrium and all of a sudden the head loss in pipe A drops, then obviously more flow is going to go through pipe A relative to pipe B, right? Because it's less resistant. But because of that, as this Q rate and the flow rate in A goes up, the velocity goes up, and so of course the head loss goes up. And so what I'm getting at here is that these systems will always naturally balance out, because if one pipe was less resistant than the other, then more flow would go through that pipe. But because more flow is going through that pipe, it develops more resistance, right? So it's always going to balance out so that it doesn't matter if water goes through pipe A or pipe B, it's going to be the same amount of head loss either way, okay? So the first relationship that we know is that the head loss of A is equal to the head loss of B. And if we expand that out, then, well, it's this, right? It's going to be friction of A times length of A over diameter of A times velocity of A squared over 2g is equal to friction of B, length of B, diameter of B, velocity of B squared over 2g. And I won't write everything out every time because it'll take longer and longer, but the point here is that we now, if we know our pipe characteristics, we now have a direct relationship between velocity A and velocity B. That's why we're interested in that. What is another aspect of head loss that we know about the system? We know something about total head loss, right? How can we define total head loss? So essentially what we have here is that the total head loss of the system, which in this case we know is 100 foot, is going to be equal to, well, it's going to be HC, right? It's going to be part of it, because we know any water is going to flow through HC, the head loss of C. And you probably now have figured out if head loss of A is equal to head loss of B, it doesn't matter which pipe you choose, but you need to pick one. So we'll just say head loss of A, because all the water is either going to flow through A, through C, or it's going to go through B and through C, right? It's going to be one or the other, but they're equal, so it doesn't matter. But we can express the total head loss in terms of one of those two flow paths. Now there's one more relationship that we can draw on in order to kind of fill in the last piece of the puzzle here. And, you know, again, if you've been watching some of these videos or studied hydraulics, you probably know what's one of the relationships we always draw on, almost always, is continuity, right? So we know that we have some total flow, right, which would usually we just say Q, but any flow between these two reservoirs has to go through pipe C. So the flow rate in pipe C is going to be equal to the flow rate in pipe A plus the flow rate in pipe B, right? And because of continuity, that means BC, AC, it's a lot of letters to keep straight here, hopefully I don't make a mistake. Velocity in A times area of A plus velocity of B times area of B. Yep. And that's just because velocity times area is a volumetric flow rate, right? So we can basically, again, if we know the pipe characteristics, we know the area. Now we have a relationship between velocity A, velocity B, and velocity C. Here we have a relationship between velocity A and velocity C. And here we have a relationship between velocity A and velocity B. So we have now enough pieces of this that we can put it back into our original equation, or between these three equations, we can solve one of these velocities and go back and solve for the other two. So let's take a look at a example problem, and I'll write it out, and then I'll give you a chance to pause the video, try to work through it on your own if you choose to, which I certainly recommend, and then we'll come back and work through it together. So let's just keep it simple, that the length of A is equal to the length of B, which is equal to the length of C, which is equal to 1,000 foot. Oops. 1,000 foot. Okay, so we also will give it, let's give it everything's the same material, so the friction factor we'll say is 0.02, and then we'll say the diameter of A is 10 inches, diameter of B is 8 inches, and diameter of C is 12 inches. Okay, that way it'll give it some different characteristics so that we'll have some different flow rates between the two. Otherwise it'd be it'd be equal between the two. Now notice we haven't given a total flow rate, right? Because if we did that, it'd be pretty easy. You would know at least velocity C right off the bat. So that's not given. That's not something we know. We really only know the pipe characteristics and essentially the total head loss, the elevation change between point 1 and point 2. Okay, so let's start with this total head loss, right? So that's going to be basically this one here, this guy. We'll start with this. Okay, so I'm probably going to run out of space on here. It's going to be a little bit of a challenge to fit all this on here. But we have 100 feet is equal to our HC, which is going to be, we'll start just expressing F as F, right? Because they're all the same. In fact, I'll just go ahead and write this out. So 0.02 times our 1,000 foot. This one was, let's do it with VA. We're starting with A. So we'll say 10 over 12 feet times VA squared over 2G. And then we'll add to that our velocity of C, or head loss of C, I should say. 0.02, again 1,000 foot, over 1 foot, times VC squared over 2G, okay? Let's go with HLA equal to HLB, head loss of A equal to head loss of B. That's going to be, again, 0.02 times 1,000 foot over 10 over 12 foot, VA squared over 2G is equal to 0.02 times 1,000 foot times 8 over 12 VB squared over 2G. Okay, so now that we can solve down, essentially we get 24 VA squared equal to 30 VB squared. And so we can say the velocity of B is equal to 0.894 VA. Okay, so now we have a direct relationship between the velocity of B and velocity of A. We have a relationship between velocity A and velocity C, and now we can put some of these together with the continuity here with the flow rates. So if essentially this is going to be for, I'll put it down here, QC equals QA plus QB is going to be BC times pi DC squared over 4 is equal to VA pi dA squared over 4 plus, now here we have VB, right? But we know that VB is this, right? So we can say 0.894 VA pi dB squared over 4. Okay. Now we can combine these together and solve it in terms of VC, right? So that's going to give us, let's see, 0.785 VC is equal to 0.545 VA plus 0.312 VA, and so VC is 1.092 VA. So now we have a direct relationship between VC and VA. Now we can take that and plug it back in. This is going to be a little bit messy. To this equation here, right? Because that's all we needed was VA and VC. So let's do that. Let's say we have again the 100 foot is equal to, let's see, I guess we'll write this out again. 0.02 thousand foot over 10/12 VA squared 2G plus 0.02 times 1,000 foot over 1 foot VC squared over 2G. And now that VC is what we're going to put in to this VC, right? So actually, let's go ahead and write that instead of VC as 1.092 VA quantity squared. Okay, so that is going to solve down to 100 foot is equal to 0.373 VA squared plus 0.311. No, I guess that was VC, but I hadn't made the substitution yet. So that 1.092 needs to still be substituted into that quantity. And then we have our 2G, right? We've already divided that out, so that's going to leave us with units of second squared per foot, which makes sense because these are going to be velocity squared, right? So that's going to be feet squared per second squared. Okay, so now if we take our VC, velocity in pipe C, in terms of A, we substitute it in for what we have for VC and solve that down, then we will get 100 feet is equal to, or actually at this point we basically have feet squared per second squared, right, is equal to 0.743 VA squared. And so if we do the square roots, divide that out, take square root, we'll have VA is equal to 11.60 feet per second. Now, all we really have to do is substitute this back in. We had this relationship between VA and VB here. It took a while to find, but VB is equal to 0.894 VA. So VB is equal to 0.894 VA, which means VB is equal to 10.37, and we know VC is equal to 1.092 VA that we have up here. So VC is equal to 12.67. Put my units on, feet per second. And that has given us all of our velocities. From there, you could go back and solve for the head loss in each pipe using Hazen-Williams equation. That's pretty simple and straightforward though, so I will leave it there for you. All right, well, I hope that was useful to some of you out there that maybe were studying for the FE or have a hydraulics class that you're want a little extra prep for the exam. Parallel pipe flow problems are obviously somewhat challenging. You know, there is quite a few unknowns and relationships that have to be developed so that they can be solved, but I think they're one of the more interesting types of pipe flow problems. So hopefully you found that interesting and useful. And again, before we go, we just want to really give a heartfelt thank you out to our entire high water community, people that have either, if this is your first video, welcome. If you've been following this for a few years or whatever, we really appreciate your support. So thank you, and we'll see you on the next one.